First off, huge thank you to Voxel 51, in particular, Jimmy and Dr. Marks for hosting us. It's an awesome event and really appreciate the opportunity to be here. My name is Michael, and in this talk, I'm excited to share with you an overview of the state of foundation models for healthcare, in particular, data stored in electronic health records or EHRs. Quickly, just a little bit about myself. I'm Michael on the slide. I'm a computer science PhD student at Stanford right now. I'm co-advised by Nigam, Shah, and Chris Ray. And my research focus has been on using foundation models to benefit hospitals and patients. As a brief outline, I'll start with some background on foundation models, EHRs, and their intersection, then walk through a couple example models, and finally discuss some of the challenges of evaluating them. If you're not familiar with healthcare, hopefully this talk will inspire you to consider applying your machine learning skills to the field, since it's incredibly rewarding and there's a ton of great opportunities. And if you're coming from a healthcare background, hopefully this talk gives you a better sense of where the field of ML is when it comes to EHRs. Before diving into the models, I wanted to just take a few minutes to make sure everyone is on the same page when it comes to foundation models and EHRs. So first off, what is a foundation model? A foundation model is basically a large AI model that is trained on a large amount of data in an unsupervised manner, which means you typically don't have to manually label the data. And what distinguishes a foundation model from a traditional machine learning model, I'd say, are two key aspects of it. First is the sheer size of some of these models, often billions of parameters with hundreds of gigabytes of training data. And the second is the ability of these models to adapt to a wide range of tasks that they might have never been explicitly trained to do. And that's kind of what you see on the right-hand side of this page of all these great emergent capabilities coming out of a single unified foundational model. So just to make this concrete, as an example, here's a screenshot of OpenAI's homepage, which lists all the various things that ChatGPT can do, things like writing SQL to translating language to classifying tweets, even though the model itself was simply trained to predict the next word in a sentence and was never trained to do any of these specific tasks. And so it would be really cool if we could leverage the power of something like ChatGPT, but specifically for healthcare and for helping patients. And there's a ton of tasks in a health system that a foundation model could help with, and that hospitals really do need help with today. So here is just kind of a brief smattering of things that a hospital might care about, things like predicting disease diagnoses, to selecting optimal treatments for patients, to stratifying people based on risk, in addition to a lot of operational concerns like resource allocations, predictions for quality metrics like readmissions, and things like that. And I'm definitely not the only one thinking that foundation models might be useful to hospitals. If you've been reading the news lately, I'm sure you've seen the many headlines about hospitals interested in deploying things like GPT-4 and other foundation models into their workflows. And there's definitely been a lot of excitement here, which brings me to the second half, actually, of this talk title, which is the EHR component of it. So for those who aren't aware, an EHR, which stands for an electronic health record, is basically a digital record of everything that a hospital knows about you. So as you can see here, your EHR will contain things like your diseases, medications, your lab test results, CT scans, MRIs, medical history, et cetera, et cetera. And while the actual so this is kind of the data that we're working with when I say, a health system, clinical data, foundation models for healthcare. The EHR is the core piece of data that we're working with. And so obviously, this user interface is kind of overwhelming, but the underlying data structure that we care about is actually pretty simple. And you can think of it basically as this diagram here, which is simply a timeline of events happening to a patient over time. And so this diagram is basically the core mental model that you should have when someone says, I'm using EHRs for machine learning. All they mean is basically a timeline of events that happen to a patient. And so there can be a lot of different types of these events, right? So in this picture, each row here is a different type of clinical event. So you might have insurance claims at the top, ICD codes, diagnoses, You'll have medications, you'll have doctor's notes and things like that. Each occurrence occurs at a specific point in time. So that's what all these color squares are representing. And so as you can see, lots of different things can happen to a patient, but, the key representation is basically a sequence of things happening over time. That's what an EHR is at its core. Cool. So now we've got both terms down. And before diving into the meat of the presentation, I want to also just make one very important clarification that I think will be helpful for people kind of understanding where this talk comes into play. Zooming out a bit, I'd say there's two main types of foundation models for EHRs that you might see. And unfortunately, I'll only have time to discuss one of them, but I'll briefly mention both. So the first is what I'll call a clinical language model, or a CLAM for short. And this is just a large language model that is used to process text that was written by a doctor. So examples include, ChatGPT, GPT-4, if they've been provisioned at your hospital, as well as domain-specific models like Gatortron or MedPalm from Google. But I'm sure we can all agree that GPT-4 has probably gotten enough publicity already. So in this talk, I'm actually going to focus on the other type of foundation model for EHRs, which are trained on the structured data within the EHR. So these are things like medications, lab tests, diagnosis codes, procedures, etc. I'll call these foundation models for electronic medical records FEMRs, FEMRs for short. I'd argue that they're potentially actually more impactful in many ways than clinical language models in the near term, even though they're definitely less studied and less covered in the news. This is basically going to be the focus of this talk. And again, if we're looking at our EHR, our patient timeline, I'm going to be focused on the top portion of this, which is the structured codes that are included within the EHR. Just to also give a sense of why you might prefer a FEMR over a clinical language model. I won't go into too much detail, but there are several advantages that come with working with structured data over clinical text. For the first, the structured data in the EHR is a much more distilled view of the patient, while clinical text is very messy and noisy. Additionally, the data sets that we have of structured data are much easier to de-identify and share. And so they can be orders of magnitude larger than data sets of clinical text, most notable example being insurance claims data sets. Obviously, the vision would be hopefully to move towards multimodal models, but there's still a lot of juice we can squeeze out of these structured EHR models. So just to tie kind of everything together then, I'd say the guiding claim of this line of research and this talk is as follows. Basically, we want to train a foundation model on the unlabeled EHRs of millions of patients in our hospital's database. So this big, huge gray circle on the left. We want the foundation model to learn common patterns of human health and disease. And then we want to be able to adapt that foundation model to a wide range of downstream tasks where it might be impossible to train a traditional machine learning model. So to make that concrete, let's say you wanted to do early detection of pancreatic cancer at Stanford Hospital. Well, at Stanford, there's actually only a few hundred patients who have this diagnosis, which makes it very difficult to train an accurate machine learning model on this small data set, let alone a model that would generalize across race, ethnicity, and age. So the key insight and the key hope with these foundation models, though, is that, at the end of the day, pancreatic cancer patients are also humans, right? And so it seems reasonable that instead of ignoring these other millions of humans that we have data on, we should be able to leverage patterns learned across a vast data set of millions of other humans to make better predictions for the specific cohort of humans that we care about, which in this case might be pancreatic cancer, but you could think of, a million different downstream tasks that a hospital might care about. So that's kind of the vision and kind of why we're interested in foundation models for EHRs. And so that brings me to the next portion of the talk, which is how do we actually do this? So we'll take a lot of inspiration from the field of natural language processing, and we're going to model the EHR as a sequence of tokens, which is something that I was hinting about a little bit before. So in natural language processing, right, the typical pipeline is you'll have a document of text, you'll split it up into a bunch of words, and you'll model it as a one-dimensional sequence of tokens. And we can do the same thing with EHRs. But this time, our tokens are no longer words, but they're going to be clinical events like ICD codes or CPT codes or medications. There are definitely a few important differences to keep in mind, though, between EHRs and text, which makes the translation not 100% obvious. The first is that clinical events are grouped into what's called a visit. So a visit is just the time period in which a patient is actually at the hospital. You can think of them as basically the equivalent of sentences. But the main difference, unlike sentences in English, is that the ordering of events within a visit can be random and doesn't actually have to matter. So like what you see on the screen here, where you have ICD code A, medication A in visit 1, could equivalently be represented as medication A, ICD code A. And the reason for this is that a lot of structured data isn't actually coded up until the end of the visit. And so the ordering within a visit is kind of arbitrary. So, there's that kind of nuance that you want to take into account. The other thing is that clinical events occur in time and events can overlap, unlike words. So for example, someone with type 2 diabetes might concurrently be suffering from anemia, right? And so you want to be able to model that sort of temporal aspects of the EHR. So, while EHRs and natural language are definitely similar on the surface, clinical events are like words, visits are like sentences, patients are like documents. There are also a lot of important nuances that we want to keep in mind when we're trying to translate some of the tools from other machine learning fields to the field of EHRs. And I'll just very quickly list a few of those nuances. I briefly mentioned some of them on the previous slide. One big thing is sequence length. It can be extremely variable for patients. For example, a prolonged visit to the ICU can generate tens of thousands of data points for a patient, which becomes a problem when you're trying to fit these in the context window of a transformer. Second, while English is always ordered left to right, clinical events can be overlapping or have unknown orderings within visits. Third, there's a lot of metadata associated with clinical events. So, when you see the word the, you're looking at the word the. When you see a clinical event, there could be a whole host of information. For example, the numerical results of a lab test or the actual contents of a clinical note that your model should be taking into account. Fourth, there's this temporal aspect, which I also previously touched on, that's not present in language, that is present in EHRs. And lastly, EHR data, like all healthcare data, is noisy, it's sparse, it's oftentimes incorrect. It would be like if someone randomly crossed out words in the book you're reading. And so you want to be able to take that into account when you're modeling. So then how do we represent EHRs for machine learning? Well, it's not quite perfect, but we're basically going to try to translate as much of the machinery as we can from natural language and do some embeddings with a few adjustments. So, first, if we start with the EHR, which, represented here is a sequence of codes where D1 and D2 are different clinical events that happen to a patient. And we're going to separate visits with a separator token, the SEP. We're going to first embed each code with some unique embedding associated with the code. And then we're going to try to account for some of the nuances of EHRs. And so one way to do this is just with, I'd say, call EHR aware positional embeddings. So we might layer on the age of the patient. So hopefully this will take into account the temporal aspect of the EHR. We might encode visits in an order agnostic way. So here the embedding for each event is the same within a given visit. And then, we might just add all these up and then, create our EHR aware embeddings from these set of codes. And so basically kind of the goal here is to encode the EHR in a way that reflects its data generation process. And, a very easy common way to do this is basically with these positional encodings that factor in some of these temporal constraints. Cool. So now that we've turned the EHR into something the computer can understand, how do we actually end up making predictions for patients? So the first class of foundation models for EHRs that I'll talk about are Bert-style models, which are based on the bidirectional transformer from Devlin et al. 2019, but adapted specifically for EHRs with some of those nuances that I described previously. I'll use BEHRT, also pronounced Bert, as a canonical example, but the rest of the models in this family are pretty much the same. And so here's just a very quick overview of how a Bert-based model like Bert would work for EHRs. So first, we'll start with our EHR database of unlabeled EHRs. We'll do the process I described before to generate embeddings for each clinical event. We'll feed these embeddings through a 6-layer, 12-head transformer, and then we'll pre-train it using mass language modeling as our objective, just like you would with natural language. And for those unfamiliar with masked language modeling, it works basically like this. We randomly hide a token from our sequence. So this little gray masked square at the bottom, we're going to hide that token from the model. We're going to ask the model to predict what was that masked token. And then we're basically going to compare the prediction with the ground truth. And if it's correct, that's great. And if it's incorrect, then we're going to penalize the model. And that's how it's going to basically learn a better representation of the EHR. After we do this unsupervised pre-training process, we can then fine-tune our model on whatever downstream tasks we care about by adding, some sort of head to the model. For example, maybe we want to predict the risk of cancer. So, we'll add a logistic regression on top of our pre-trained model to do that sort of prediction. Importantly, though, we only want to use clinical events that have happened in the past to make our prediction. But this is pretty straightforward machine learning right here. There are several cool things, though, that come out of this unsupervised pre-training process. So just like we see in vision and NLP models, where the models learn representations that make semantically meaningful clusters, we also see that the embeddings learned by these EHR models for each diagnosis code also have semantically meaningful clusters. And so in these graphs, the coloring is like the grouping of disease, and each individual dot is an individual structured code in the EHR. And what's nice is you do see that there is clustering by colors. So there does seem to be some sort of physiological meaning that the model is learning to associate with each individual code. Additionally, because we're using transformers, we can use attention to see where the model is looking. So here's an example from MedBert, which shows that when it's trying to predict type 2 diabetes on the right-hand side, it pays a lot of attention to repeated mentions of long-term use of insulin, which checks out. Finally, and most importantly, we do see performance gains from using these BERT-based foundation models over traditional machine learning methods. So in these graphs, the orange lines are the foundation model MedBert, and the gray and blue lines are baseline models. And each plot is a separate data set. And here the x-axis is the number of data points that were used for fine-tuning the models. And so basically the trend here is we see that the MedBert model, the foundation model in orange, consistently outperforms both of the baselines across a wide range of data set sizes. Interestingly, though, the few-shot performance isn't that great, but I'll revisit this a little bit later in the talk of how we can boost the few-shot performance of these foundation models. So that is the Bert-style models. And there's a second kind of major class of foundation models for EHRs, which are those based on the GPT architecture. So using causal language modeling instead of masked language modeling. In this section, I'll use the Climber model from Steinberg et al. 2021 as a guiding example. But this section also applies generally to any sort of GPT-based EHR model. And so just as a super quick refresher of kind of what we're trying to do, our goal here again is basically we want to train a model on lots of patients. We want to apply this one model to many downstream tasks. And then we want to get the benefits of foundation models that we see in other fields. So things like higher accuracy, but also things like few-shot learning and task adaptability, which we saw inklings of with some of those initial BERT-based models, but definitely seem to be more juice to squeeze. And so here is how a GPT-based architecture would work for EHRs. So specifically with Climber, what they did was they took an EHR database of about 2.5 million patients. They embedded them using the process that I described previously. They fed these embeddings through Climber, and they used the next token prediction objective. And basically how this works is, again, we have our patient timeline. We're going to mask out the last code in the timeline. We're going to ask Climber, hey, which code do you think comes next in this timeline? It's going to make a prediction, and then hopefully it gets the right code. And if not, then we penalize the model, and that's how it learns. And so the key difference here from those BERT-based models, right, is that here the hidden code is always at the end of the sequence, whereas with BERT, it could be somewhere in the middle, which allows this model, Climber, to do generative modeling in a way you couldn't do with those BERT-based EHR models. So from this, we again get a representation for our patient, in this case, a 768-dimensional embedding vector, which theoretically, represents all the information about that patient up to a particular time point. And then just like with BERT and MedBERT, we're gonna train a small linear head on top of these embeddings and apply it to a bunch of downstream tasks that a hospital might care about. And so what do we get out of this? Well, again, we see better performance over traditional machine learning methods. But what's interesting now is we see this in both high label and low label settings. So in this plot right here, the foundation model climber is in red. And again, the x-axis is the number of examples we're using for fine-tuning. And so here we're seeing consistent benefits in low label settings and more indication that the model is capable of few-shot learning in a way that other models aren't. Additionally, we're seeing better performance across a much wider range of downstream tasks, from things like predicting 30-day readmissions to abnormal lab value detection to chest x-ray findings. And in these middle plots, sorry, just to confuse you, the foundation model is actually in blue now. And so the blue model, or you want the blue line to be higher than the red line in the middle plots. And then finally, on top of being more accurate on more tasks, we also see better robustness to data shifts across time and subpopulations, which is very important in healthcare. And that's kind of the plots on the right-hand side here. I'd say overall, it seems like these GPT-based models tend to perform better than the BERT-based ones on prediction tasks. And that seems to be because the training objective of next token prediction seems to be more aligned with predicting future state than the mass language modeling objective, because it relies on future information during pre-training that is not available to the model at test time. So we see slightly better performance with some of these autoregressive formulations. I would definitely encourage you to read these papers to get more insight on these claims. But hopefully, what I've convinced you through these very quick run-throughs of the two different main styles of foundation models for EHRs is that foundation models do yield benefits for prediction making in healthcare and on tasks that a hospital might care about. So just to recap, we first discussed BERT-based models in which we treat the EHR as a sequence of tokens and apply mass language modeling, where we're basically predicting, what is the probability of a specific code at a specific location in a patient's medical history. Similarly, we looked at GPT-inspired models, which use causal language modeling. Again, we're trying to predict what the next code is. But I don't want to leave you with the impression that machine learning for healthcare is just porting over BERT and GPT-2 to EHRs, because there's actually a ton of opportunity to leverage the unique richness of EHRs for better predictive modeling. And this is just a very brief taste of what's out there. So I'll briefly mention one such effort. It's called MOTOR. It's also by Ethan Steinberg. And it uses a time to event modeling objective instead of next token prediction or mass language modeling. The key difference is basically, instead of trying to predict the probability that we see a code, instead MOTOR tries to predict the time until we see that next code. And so instead of making binary predictions, does this code occur or not, we're going to instead estimate a probability distribution of when that code might occur over time, which is inherently a more challenging problem, which takes more full advantage of the temporal information in EHRs. And we do actually see that this objective yields significantly better performance on prediction tasks with medium and longer term horizons. And so, there's lots of additional knobs that you can turn with these models to make them more adapted to the peculiarities of EHRs. And definitely happy to chat offline about interesting research directions, but just wanted to give a taste of, some of the research directions that people are actively exploring here. So now that we have a sense of, how we build these foundation models, how do we actually know whether they're good or not? Unfortunately, that's been a challenge that's plagued the field of ML for healthcare for a while. And I would argue that it's suffering a little bit from a bit of a reproducibility crisis when it comes to foundation models. So we recently did a survey of all of the published foundation models for EHRs that we could find. Of the 34 that we found, only 25 released their code publicly. So this is just bare minimum GitHub repo. Can I see the code that someone ran for this paper? Of those 25, only 4 released the weights of the model. And of those released weights, none of them were accessible via common machine learning libraries like Hugging Face. So it's almost impossible to build off the findings of other researchers or to simply validate that someone's model does what it says it does. So, before I showed you this slide, which was the purported benefits of foundation models for EHRs, but I was kind of hiding the ball here a little bit, because even these papers suffer from pretty substantial limitations. Their evaluation is typically only done at a single hospital. They test on a very narrow set of tasks. And most importantly, the models that they test are not publicly available, which means it's impossible to build upon their results. But, this is not for a lack of trying. In fact, a lot of benchmarks for EHR data currently exist. And the citations listed here are actually really well done. But just like a model is only as good as its data, so too is a benchmark. And it's been very difficult to release EHR data for research and public use, as I'm sure you can imagine. And so a lot of these benchmarks are drawn from basically the same exact data set. It's called MIMIC-3. It's about 40,000 patients taken from a single hospital. And it's entirely focused on two departments, the ICU and the emergency department, which is a very narrow picture of the type of data a health system would have on a patient. Additionally, a lot of these benchmarks only evaluate on a handful of tasks, which makes it difficult to verify one of the main benefits of foundation models, which is task adaptation. And they're not geared towards few-shot evaluation, which again limits our ability to test one of the core value propositions of foundation models, which is low label settings, few-shot learning, et cetera. And then finally, I already mentioned this, but basically none of these benchmarks publicly release their models, which makes it very hard to build upon their work or validate it. And so to help address some of these issues, we recently released a new benchmark called Earshot, EHR-SHOT, which I will now be shamelessly plugging for the next few minutes for people to go check out. And basically, Earshot is a data set containing the full longitudinal EHRs of about 7,000 patients from Stanford Medicine, as well as the weights of a 141 million parameter foundation model that we pre-trained on 2.5 million patient records. And basically, the goal of Earshot was to fill a lot of the gaps in this table. So not only do we have the ICU and ED, but we also have the full longitudinal health record of patients over many, many years and sometimes even decades. We include 15 clinical tasks. We do few-shot evaluation, and we also publicly release the weights of the model that we trained. Just to give a sense of how do you make one of these data sets, basically we start from Stanford Hospital, we take a cohort of 7,000 patients, and then we label all of their EHRs for 15 clinical tasks, ranging from operational concerns like readmissions risk prediction to lab test prediction, to predicting new diagnoses, to chest x-ray findings. So a pretty diverse range of tasks. And then at the same time, we take 2.5 million patients, take their EHRs, and we pre-train a foundation model based on the climber model that I previously mentioned. And then we publicly release the weights of that so that other people can both fine-tune that model on their own private EHR data sets, as well as potentially continue pre-training them. And we also have some tutorial notebooks at this link that I'm happy to share in the chat as well, if people want to play with this code or port it over to other public EHR data sets like MIMIC-3 and MIMIC-4. In this work, in addition to releasing the data set and benchmarks, we also actually test our model on the 15 tasks. And what's promising is that we see in these extremely low label settings. So previously, the graphs I showed you were like 100 examples, 500 examples, 1,000. Here we're going all the way to 2-shot learning, 4-shot learning, 12-shot learning. And here the blue line is the foundation model climber. Here we do see substantial gains from using a foundation model that was pre-trained on lots of patients over the most competitive baseline model that was not a pre-trained foundation model. And so this is very encouraging. And we release all the code and data for this so that hopefully people can actually replicate all the plots that we have in this paper. And so if you're interested in working with any of this data, if you're a healthcare researcher interested in testing your models, I would highly recommend checking out the GitHub repo that we have called Earshot Benchmark, where we have all the code for pre-processing, running the models, and evaluations. And then you can download the data set at the Stanford AMI Center at this link. I will say we're still in the process of finalizing the actual full data set release. So there's only a small sample right now, but hopefully in a couple months, we will post an update on our GitHub page and website, and you'll be able to download that full data set if you sign a data usage agreement, which is just kind of a standard research thing. So just to very quickly summarize in the last couple minutes, hopefully I've convinced you that foundation models can offer significant benefits to hospitals. Not only are they more accurate, but they require fewer labels in a lot of cases, which, as you can imagine, it's very expensive to get doctors to label data sets for healthcare. So fewer labels is always good. It simplifies model training because you can just reuse the weights that I've already published instead of training your own foundation model from scratch. It simplifies the deployment of these models, and it also improves their robustness, which is, again, a key concern in healthcare settings where you want to make sure that your models are reflective of the diversity of patients that you're treating at a hospital. At the same time, though, one of the challenges with a field like this is I always feel like not enough people are working in the space. And there's kind of three main challenges that I see, which is often a roadblock for people. The first is, the modeling side. What is an EHR? How do they even work? The second is getting access to data. And the third is, the reproducibility stuff that I mentioned before. Hopefully this talk gave a little bit of insight into how to start thinking about modeling for EHRs. And there's plenty of great resources that I'm happy to point people to get, an initial start in how to think about modeling this unique form of data. In terms of data set access, like I mentioned before, there are a few great public data sets available to people doing research, such as Mimic3 and EICU. And now the one that we just released, which is Earshot, which contains full longitudinal EHRs. And finally, reproducibility, still definitely an issue that models aren't publicly shared like in other fields. We don't really have a hugging face for EHRs quite yet, but we hope that Earshot will be an initial first step in that direction. Finally, just would like to conclude by thanking all my lab, funding sources, Stanford Healthcare, NSF, and the Amy Center, and also Jimmy Jake and Voxel 51 for hosting this talk. So yeah, really appreciate it. And yeah, happy to chat offline with folks if you have any questions. My email is here. Please don't hesitate to reach out.
All right, awesome sauce. Thank you, Michael. You've got four questions in the Q&A if you want to toggle over
Awesome.
to the Q&A queue.
Yes. Okay. First question. You mentioned wearables. How is it treated in the EHR? Great question. So I'd say, unfortunately, wearable data isn't actually really integrated into EHRs yet, but that is something that we'd be very interested in working more towards. So yeah, I'd say it's a data modality that has not gotten significant attention yet. But yes, you would usually treat those as just, like a vital sign or like a biomarker over time. Can these models estimate the probability of an event that has not happened yet? So yeah, so I'd say like a great example of that is the motor model that I mentioned, where you're basically estimating the time to an event, where if the event doesn't happen, the time to the event will just be, 1,000 years or something. But if the event is predicted to happen within some reasonable window, what's cool about the time to event modeling is you'll basically get a distribution over time of how likely will this event occur after a certain amount of time. How effective are embeddings in preserving the diverse range of information found in EHR records, especially considering that these records consist of not just categorical values, but also numerical and textual data? Yeah, so that's a great question. I think the answer is right now, a lot of the methods that I described do not take full advantage of the metadata that I had mentioned before that you have noted in your question, right? Like the lab value results, like the contents of the note, the provider who wrote the note, things like that. So I'd say there has not been a lot of work in that. People just baseline assume, hey, these are categorical values and we'll embed them all one hot. But I think that's a great research direction. And I think moving towards more multimodal stuff will help in the future. So I think that's a great question, and I don't think it's solved. You mentioned that codes within a visit can occur in any order, but for trained foundation models, are all the codes within a visit ordered in a certain way before training? For example, ICD codes, then notes, then medical records. That's a great question. The answer is it depends on the hospital. Some hospitals do have like a prioritized listing of codes where like the most important ones come first. Other hospitals, it's totally random. Other times, the codes will be entered a certain way and then changed post hoc when they do the actual billing. So the answer, yeah, the short answer, it depends on the hospital. But I'd say the general answer is you can't really rely on any sort of semantic ordering between the codes, unfortunately.